Um, a brief discussion of kinetics versus thermodynamics. You should be able to read these energy diagrams, and we will apply them to new reactions that we learned throughout the semester. But just very generically, if you have a reactant here forming product, there are multiple steps to the mechanism as shown along the way. And the transition states, right, here we have energy maximum transition state 1, transition state 2, and transition state 3. There are 3 transition states, which means 3 mechanistic steps, right? Or in a mechanism, that would be 3 arrow pushing events, where you would show bonds forming and breaking. The number of steps in a reaction is the number of barriers you must cross. The energy minima here are intermediate. So this is intermediate 1, intermediate 2. If there are 3 steps, there's always 1 less intermediate, right? Intermediates between the steps. The overall reaction, right, or the free energy change on the y-axis is the Gibbs free energy of the product minus the Gibbs free energy of the reactant, or delta G standard. Here, that's negative or exergonic, which thermodynamically tells you about the reaction's favorability, or the products are more stable because they're lower on the y-axis, they're lower in free energy. And the reactants are less stable, or they're higher in energy, okay? So that's thermo. The reaction's exergonic, or delta G, drops down, and it's product favored. And that means, because delta G is related to the equilibrium constant, okay, it means that the equilibrium constant must be greater than 1, or it must be more products than reactants at equilibrium. So equilibrium is another way of saying which side is lower in free energy. The side that's lower in free energy, that's more stable, the products will be more abundant, or the equilibrium will favor the right. So we get that from the thermodynamic parameters, okay? But then there are also kinetic concerns, which tell you about speed for a reaction, okay? So if you think about stability next, for reactants as compared to intermediates, as compared to products, right? If you decrease the free energy, then you increase the stability, right? Lower energy means more stable. So as shown above, the products are lowest in energy. The next lowest is the reactants. And then intermediate 2 is a little bit lower than intermediate 1. So I'm just ranking them according to their standard free energies, which are given to us. So in other words, stability, most stable, or product is the lowest energy, and then reactant, and then intermediate 2, and intermediate 1, right? And the product being the most stable of any of these is why it is product favored, or equilibrium constant is greater than 1. The most reversible step, okay, is the one where KQ is closest to 1. Not for the whole reaction, but for that step. And if KQ for that step is closest to 1, then delta G is very close to 0. And because the free energy of the intermediates, intermediate 1 and intermediate 2, they're pretty close in energy, right? This difference here is much smaller than the difference between reactants and intermediates, or the difference between intermediates and products. This step is the most reversible, or the intermediates reverse back and forth until the reaction reaches equilibrium. Okay, so the two that are closest in free energy or delta G, the change in free energy is the smallest. I should say smallest instead of 0. That will give the most reversible step. So because the free energy of 2 was not too far from the free energy of intermediate 1, it is step 2, or going from intermediate 1 to 2, that would be the most reversible. And then the smallest rate constant, which means the slowest, recall that rate constant is little k, not equilibrium k. Okay, if you decrease little k, you decrease the rate. The step with the smallest rate constant should be the one that has the highest activation energy, or the highest point to reach the transition state. In other words, the least stable transition state will be the hardest one to cross, and therefore the slowest. Go back to the graph above. If we're going in the forward direction, the highest barrier we must cross is transition state 1, is the highest free energy, or the activation energy is the barrier that we must gain, or we must overcome endergonically, which means this is the rate determining step, or that's the step that will dictate the product you get under kinetic control. So these ideas of activation energy and speed and rate constant, they're based on how high the barrier is. Okay, and that tells you if it's fast or slow. The thermodynamic parameters are final minus initial, or only depend on start and end. And they don't know anything about how long it took to get there, or how high the mountain is that must be climbed. So this is step 1 that was slowest, or has the highest activation energy. So please be comfortable labeling those, and you could be asked to draw one or label one on the exam and apply it to some of the new electrophilic addition reactions that you've been learning.